There we go. Okay. So we're going to tie all this stuff we're doing back to the whole beginning of the course. And so let's review from the beginning of the course. So over here is a rate of change of elevation function from the border, and the units on this are 100 feet per mile. And then this is miles. And this is miles. Okay, and so let's find, and then the blue is the actual rate function, the true rate function, and then we have an approximating step function, rate function, with delta x at 0.4. So our delta x is 0.4 miles. And so approximate the change in elevation starting at, say, 0.8 miles from the border to, say, 2.1. So can you approximate? The net change in elevation from 0.8 miles to 2.1 miles from the border. Go, see if you can do that. And I'll label these here. I'll label these steps as R1, R2, R3. Right, and the 1, 2, 3, 4 has nothing to do with how many miles, right? It's just saying the first and the second and the third. It's just an index. It's just counting. So we're going to approximate the net change in elevation from 0.8 miles from the border to 2.1 miles from the border. Go. You can do it. Everyone should be able to do this. Can you do it?
Yeah.
So is that a yes or a no?
It's kind of a maybe.
Maybe. I'll be able to do this.
Yeah, I did that. Yeah, I never thought that.
Okay, who wants to give this a shot? Steve, tell me.
We got a 350.
Oh, no, I want an expression.
Oh.
We're not calculating anything.
Well, alright, 350 plus 300.
No number. Oh, sorry. No numbers, you guys.
Okay.
This is an expression that would approximate this. So no numbers at all. I mean, except for delta x. So what would it be?
The summation of your rates times your delta x.
Okay, so be specific. Go ahead and do it.
R3 plus R4.
R3.
Plus R5.
We adding the rates together?
Well, I'm just factoring out.
Don't factor out.
X. Okay, well, R3 delta x plus R4 delta x. Plus R5 delta x plus and then the remainder will be 0.1, or you can see, just the remainder.
So what's the last term?
Rate times delta x minus the rate, I don't know,
What does that number represent? What?
your last interval
Okay, so this is, here's 2, and then here's 2.1.
times 0.1.
0.1. Yeah, and so for delta x's, you could have put 0.4s in there. Okay, is this what you did? This is what you should have done, right? So k delta x plus k delta x, right? Bits of accumulation. This is the rate, and so we're summing up these bits of elevation change. Question?
Isn't the 0.8 with the R with the rate change with the R2?
What's that?
Why don't we start at R3 when?
So we're starting at 0.8.
Yeah.
So how are we approximating the rate in this first interval from 0.8 to 1.2? What approximates the blue curve? Here, R2 or R3?
And if you directly go up, isn't it land on R2?
No.
No, 0.8.
No, but so you're not approximating at a point. You're approximating. We're generating the change in elevation over this interval,
Okay.
right? So what's our approximating rate in this first interval? Yeah, R3, right? Yeah, so this is all R3 through here, and then R4, and then R5, and then we have a partial interval 0.1, R6. And that would give us the net change in elevation, or an approximation, okay? How can we do that same thing using this approximating accumulation function? So how can we use the approximating accumulation function to get that same thing? Ryan, or Brent, go ahead.
Can you do A of 2.1 minus A of 2.8?
You want A of 2.1 minus A of 0.8? Is that what you said?
Yeah.
0.8. This is where we started.
I was just confused because it says
Oh, I wrote everyone wrong. Sorry, guys. Yeah, I drew 8 and I meant 8, but then I wrote 0.04. Okay, so we've talked about that. So our accumulation function. So A, what is A of 2.1? It's the total accumulation of elevation from the border up to 2.1. But if we just wanted the change starting at 0.8, we're going to subtract off the total accumulation of elevation in the first 0.8. If we subtract that accumulation, then we get, well, here's something like this to this one here. So then the difference of these elevations this would be this value that I'm doing A of 2.1 minus A of 0.8. It's this change in accumulation. Okay, so now I'm going to make delta x really small. Maybe. Why is there a hand there? Shouldn't be a hand. Okay, that's fine. All right, so now I'm going to make delta x 0.03. And I'm going to turn off the actual rate function. So we're looking at, this is still the approximating function there in black, or purple in black. Okay? So now, this is just representing a very small delta x. Okay? Do it again. So write the, in two ways. I want you to write the net change in elevation from 0.8 miles to the border to 2.1 miles from the border, with this situation representing very, very small changes in x. Might be able to get even one more smaller. There we go. That's 0.01, all right? So that is still actually a step function, but delta x is so small, so we virtually have the exact rate.
Where it's articulated. Where it starts and where it's D2.
Okay, Alexander, what do you think?
I got the integral from 0.8 to 2.1 RT dt.
The integral from 0.8 to 2.1 of
RT dt.
RT dt. What do we think? Yeah, so when delta x is sufficiently small, that's what I'm trying to represent here, and you can see that that is virtually the exact rate graph, even though we got very, very small steps. Then we remember that our accumulation we did with an integral, and so we see kind of the same thing happening here. How do we see in that expression, how do we see this? So how does this summing up all these relate to this expression? What are the similarities?
We have well, we have a rate compared to a change in x.
Times, right? So what does that right there represent?
Small bits of accumulation.
A small bit of accumulation, right? That's an R delta x. Each one of these is this, okay? And then what about the integral sign?
The sum.
Sum. That's a German S, means sum a bunch of them up. And we're going to start at 0.8 and end at 2.1. Okay? Is this open form or exact form of open form or closed form of accumulation?
Close.
Open or closed form of accumulation? I said closed. Agree with that? Nope. What was the difference between open and closed form? Open was reflects Ross. Reflects the process, right? Open reflects process. It's showing us the sum of many bits of accumulation. So this is open form. What is closed form like? What's closed form? What's that? Yeah, well, but what does a closed form function look like? What was closed form function? Just like our standard functions, right? Like sine and x cubed and e to the x, right? So our closed form functions are the functions we're familiar with that just generate lots of outputs. We just rapid fire inputs and they generate outputs. Okay, that's closed form. So this is open form. Is this exact or approximate accumulation? So it's exact and it's open form, right? Okay, what about over here? So now suppose that the true elevation function is e of x. How can we represent, using the e function, this this open form exact accumulation? How can we do it using the e function? Kaylin, do you know?
Wouldn't it be e of 2.1 minus e of 0.8?
That's right. And is that exact or approximate?
That would be exact.
And is it open or closed?
Open.
Open. He says open. Agree with that? So this, what kind of function is this E function?
Exact accumulation.
Exact accumulation. But it's like a if we had the function for this curve, it'd be like a closed form function. So this is like our closed form over here. Okay, so now suppose we're starting at, this is getting a little messy, sorry about that, but suppose we start at any value C and we accumulate to our changing value X. So what would the exact accumulation be starting at C to any roving value? So X can be roving here. So it's like we're doing an accumulation function. So this is an amount, right? So this is an amount of accumulation. But now if we let that right endpoint change, we have an accumulation function. So what would the exact open form accumulation of elevation be starting at C up to X? What would that be? Aaron?
A of C minus A of X minus C.
So are you trying to write it by the left side or the right side? You changing your mind? Okay. So I want the open form exact accumulation function if we start at C miles from the border and go to X miles from the border. Yeah.
Integral of C to X or RT dt.
What do you think? That's right. Okay. And now we want to use the elevation function to write that same accumulation function. What would it be? Yeah.
So just E of X minus E of C. Good question.
Please.
For the open form, is there a difference between putting R of X dt or RT dt?
Yes. Because what does X represent in our accumulation?
That moving.
It represents where we stop accumulating. Okay? It's where we stop accumulating. So why do we need a different variable there? We need a different parameter there. Because what does this represent?
The rate at any point.
It represents the accumulation. We have to accumulate up these little bits of elevation by letting the value increase from C up to X. So if we put X in there, the only thing we're going to get is the rate at the end. So we need a different parameter saying all the X values in between C and X. Make sense? Okay, now, what's the relationship between this function and the rate function? What's the relationship between E of X and R of X? Somebody new. Austin, what do you think?
It's the exact accumulation function for that rate function.
Okay, that's true. So how are these related relative to things we've been talking about recently in the course? How is that function and those functions related? I know Alexander knows. Janae? Is one of them the derivative of the other? Shayna?
Yeah.
Which is the derivative of which?
The rate is the derivative of the accumulation.
Yeah, so if this is our accumulation function, if this is the rate of change, then this is the derivative of E, right?
Wait, is R the derivative of E of X or is that the whole thing?
You tell me. So what this whole thing mean? This whole thing?
Yeah.
What is this about? So what is this times this? What does it mean? No, it's about a tiny bit of change in x.
Yeah.
Right. So what does that give us? A little bit of accumulation. So, derivative of e, is it just the r or is it the whole thing? The derivative gives us what? Rate of change. It doesn't give us a little bit of accumulation. The derivative of our accumulation function gives us a rate of change function. So it's just the r. Does that make sense? Okay, so we have this thing right here that we've, and this is all kind of review, but we're kind of moving towards. All right, any questions about this screen? Can I erase? And any questions? Okay. All right, so here's what we just said. The integral from c to x, rt dt, equals f of x minus f of c. And what is this again? This is the, how would you describe that?
Exact rate.
Exact rate. That is the exact rate. Agree?
It's accumulation.
Exact accumulation. It's the exact accumulation in
Open form.
open form. Okay, what's this?
It's the exact accumulation close form.
He says the exact accumulation in closed form. What do you think? Yeah, it's also exact accumulation, but it's based on this function f that's like a closed form accumulation function. So this is exact accumulation in closed form. Okay, so this is like the last piece of the puzzle. If we have the exact rate function, so I'm going to make blue. So if we have the exact rate function in closed form, that's what closed form rate function, can we get the closed form accumulation function? This is the last thing, the last piece of the puzzle. This is what we have not seen yet. We were able to write the open form. That's what we did. We built up this open form, but we never had a closed form accumulation. We never had an exact closed form accumulation function. So this is where we're kind of putting the last piece into the puzzle here. Okay, so if f of x is an accumulation function, what's its rate? 2x, right? Is its rate of change function. Okay, so what does that mean? Zoe, can you tell me what that means right there?
It means we're getting the accumulation from 3 to x of 2t.
And what is 2t?
The rate.
Yeah. So if there's some function changing at a rate of 2t, this is accumulating from 3 to x. Okay? And what does that equal? So now that we know what that equals.
Could be a t squared
So use function notation.
function notation.
Mm-hmm.
Would that be f of x minus f, like you're trying to say?
Uh-huh.
X minus
F of x minus
f of 3.
f of 3, right? But we know what f of x is. What is f of x?
T squared.
It's x squared. And what's f of 3? 3 squared. So the question is, so here, look, we have it. We have a closed form accumulation. We had open form exact accumulation, but now we have it's a closed form, an easy function that gives us accumulation. How is it that we were able to have that? How is it that we were able to have the closed form accumulation function from open form? What allowed us to do that? So here was our rate function. And now we've got a closed form accumulation function from that rate function. What was it that allowed us to do that? What's that? This right here. So here was our rate. The fact that we knew the accumulation in the first place. You see that we were able to, we got that rate from that accumulation function. You see? So the reason that we knew that this was the accumulation function of this rate is because we had it to begin with. We knew that if the rate was 2x, we knew that comes from an accumulation function of x squared. Okay? So how about this one? What's the rate function for e to the x cubed? Molly, can you do that one?
It's 3 e to the x cubed.
3e to the x cubed.
No, 3x squared e to the x cubed.
Chloe, you like that better? That's it. Okay, so what am I representing here? Gilbert.
You're showing the accumulation from negative 2 to x
Accumulation from -2 to x.
of the function, of the rate function, 3t squared e to the t squared.
Right. And is this, what is this, an accumulation function or a rate function?
That is well, the inside is a rate function.
No, the whole thing.
Okay, the whole thing's a rate function.
Accumulation.
That's the accumulation.
Open or closed form?
Open.
Open form of exact accumulation. So now, write the closed form of the exact accumulation. Write the closed form of the exact accumulation. Melody, did you get it?
I have f of x minus f of
That's a great start. That's it. So now can we go from there? If you want. What is f of x? It's right there on the screen. It's right there. What is f of x?
It's e to the x
E to the x cubed. And what's f to the -2?
plus e to the negative 2.
That's it. Okay, so how can we test to see if our closed form exact accumulation is correct? Yeah, so we'll graph the closed form and we'll also graph the open form. Which one do we trust? We trust the open form, right? Because we know that rate's right. But along the way, there might be some algebra work where, we might have made a mistake. So our trusted form is open form, and we'll compare it against the closed form. All right, so before we do that, and I'll leave the screen up. Anybody have a question? Does this make sense what we're doing? What's that? Okay, so what was our original function?
E to the x cubed.
E to the x cubed, okay. And what do we get for the rate function? 3x squared times e to the x cubed. Is that right? Okay, and was it from -2 we start? So does this look like a correct open form? From -2 to x of our rate dt. So let's graph that. Cool. All right, so that's the what? I just graphed the open form of the accumulation from -2 to x of this rate function. And we came up with a closed form for that. So we're going to type in the closed form just as we had it. So, Marco, what was it?
Was that
Our closed form accumulation.
e to the
E
x cubed
to the x cubed.
turn out to be e to the -8.
Is it e to the -8? Sure, okay. And so we'll do that I'll turn this one back on again. So that's the first one. So if I turn this one on and it's correct, it should land right on top, right? So we'll make it red. There it is. Okay, so we've got open form accumulation, and now we have the closed form accumulation function for that open form. And how, again, same question, how was it that we were able to get that closed form accumulation function?
We knew the e to the x.
Yeah, we knew the accumulation function from where that rate came. Okay? And so this idea of the reason we couldn't do it before is because, what? We didn't have all the mastery rules. We didn't have all the closed form rules for getting rate from accumulation. Now that we have all those rules for getting rate from accumulation, now we have a way to get the closed form accumulation from the open form. And what is it? It's like the reverse. It's the reverse of all these rules that we learned. So it's not a new set of rules. It's thinking in reverse from our set of rules that get us rate from accumulation. Does it make sense? Okay, so let's summarize that. Okay, so this is what we did at the beginning of the course. We had an exact rate of change function in closed form. We spent the whole first month and a half with an exact rate of change, and we came up with exact accumulation in open form. So write what that is. Write what that is. What was the exact accumulation function in open form, given that closed form rate? You should all be able to write that. Yeah.
It's going to be the integral of
Okay.
r of x from c to x.
Okay. It's integral. So we want to use r of t dt, and then from what to what?
Well, it's going to be from c to x.
Right. Exactly. Here I'm using a. Okay. So from a to x, rt dt. Okay, if we have an exact accumulation function in closed form, we have an exact accumulation in closed form, and we get an exact rate of change function in closed form. So relative to recent things in the course, what is this? We have an exact accumulation in closed form, and we get an exact rate of change in closed form. Taking a derivative, yeah, Alexander. Yeah, mastery exam. This was the mastery exam. We've got exact accumulation in closed form. We've got all these rules that we created to get exact rate of change in closed form. So really, over there on the left, those are both the rate of change in closed form. Okay, those are really both the same thing. So here's where we were at when we had the mastery. We could get from exact rate of change, we could get open form accumulation, and from exact accumulation in closed form, we could get rate in closed form. So the question is, what about this last? How do we get exact accumulation in closed form from exact rate in closed form? So that's how do we get exact accumulation in closed form from exact rate in closed form? Okay? Well, it's what we were just saying. It's saying whenever we know the exact accumulation function in closed form that gives us this rate of change function, then we can do it. and it comes from all these mastery rules, but like the reverse. So in order to have this gray arrow, we needed the pink arrow first. We needed these rules that got us exact rate of change in closed form from exact rate of change in open form. And so now we have the other direction. We can get exact accumulation in closed form from exact rate in closed form. Okay, so let's try another one. So set up the open form accumulation from starting at x equals 1. So open form accumulation for this rate starting at x equals 1, and the closed form. So both. So write the open form accumulation starting at x equals 1 for this rate function, and the closed form accumulation. I think it's 1. I'm crossing my fingers. But we can make an easy change if it's not. All right, so Sterling, open form exact accumulation for this rate function.
The integral from 1 to x of 24t cubed times e to the 6t to the 4.
What do you think? Did you get it?
Well, instead of t's would be x's.
You want to? What are we reserving x for? X is where we accumulate 2, right? It's where we're accumulating 2. So we need those t's. There was one little thing that he missed. dt, right? dt. Good, it is 1. I guessed right. Okay, how about closed form accumulation? Jonathan, we'll try closed form accumulation.
It's e to the 6x to the 4th
Right?
minus e to the 6 to the 4th.
You're thinking it right. The last thing you said wasn't right. You're thinking the right thing. It's not 6 to the 4th, right?
6 times 1.
6 times 1 to the 4th, which is just 6, right? Yeah, so it's f of x minus f of 1, which is what he said. E to the 6x to the 4th minus e to the 6. Okay, another one. So let's do the rate function first. Rate function for this one. Who knows their rate functions? How about Connor? This Connor.
It's gonna be 1 over 2 times the square root of e to the negative x squared.
Huh? Is that it? It's a good start. But we got chain rule, right?
That's gonna be multiplied by
Multiply by
to the negative x.
e to the negative x squared. Got it? Still some more, right? It's a triple chain rule. Go ahead, Gilbert.
Times negative 2x.
Times negative 2x. Okay, so we got it. So let's simplify that to make our life a lot easier. So the 2's can go, right? And so notice that this is like, right here, this part here, the left, is like A over radical A. What does that equal? A over radical A. That just equals radical A. So we still have that x, right? So this whole thing becomes x times, or negative x times square root of e to the minus x squared. So that is our rate function. So write it in open and in closed form, exact accumulation, starting at -2. Okay, this counter over here. Open form.
The integral from root from 1 to x.
Starting at -2.
Oh, the 2 to x.
Okay?
Negative t square root e negative t squared dt.
What do you think about this open form? Exact accumulation. Like it? Okay, what about closed form? Nicholas, want to try?
F of x minus f of -2.
Okay, which would be what? Let's just go right to it.
E to this, no, wait, let's start. It's root of e to the minus x squared.
Say it again.
Root of e to the minus x squared
Okay.
minus the root of -2 to the, oh no, e to the -2 squared.
How do you do?
Negative 2 squared.
Oh, right. A negative here too? Yeah, it's tricky. Yeah, Chloe.
Why aren't you multiplying positive 1 by -x and then
Say it again? Oh,
-2? So there's that t in there, and then -t times the square root of e.
okay, but what is this? Is this accumulation or rate?
Oh,
So it comes from our accumulation function, right? Yeah. Are we good? So let's check this one on graphing calculator. And then, can I erase? Last chance. Okay, so what was our original function? Square root e to the negative x. And for our rate, we got negative x times this, right? Copy and paste. How's it look? And it was at -2? So let's look at the, this is the open or closed form that I'm showing?
This is close.
Open or closed that I'm graphing right now? Open, I'm graphing the integral, right? I'm graphing the integral, so that's the open form, accumulation. And now what do we get for our closed form? Ryan, tell me.
You want a graphing calculator, or do you want me to just say what it is?
No, no, we're gonna put in what we got algebraically to check it.
Okay, so this would be the root of e to the negative x to the 2.
Right?
Minus the root of e to the negative 2 to the 2.
So what would that be? E to the what? Ends up being
e to the negative
e to the negative.
2, 4, I'm sorry, 4.
How's it look? Is that what we came up with?
It's not negative. 'Cause it's
Negative 2 squared is positive 4, but then it was negative x squared, right? Let's take a look. Got it. Okay, question. The fact that what do you notice? Where are we starting accumulating from?
negative 2.
Negative 2. What do you notice relative to that in this graph?
Looks like there's
So focusing here on our starting point of accumulation, negative 2. What do you notice?
X is 2.
Christian?
There's zeros at negative, there's a 0 at negative 2.
There's a 0 right there, right? So how do we make sense of that? Does it make sense? And if so, how do we make sense of it? Peter?
Well, you just start accumulating after that. So you just start gathering area on the curve after -2.
Okay? Or accumulation of quantities. So if we're going to start, if this gives us the total accumulation starting at negative 2 to x, then at negative 2, we zero accumulation. Zero accumulation, right? Okay? So if I change that to negative 1, what's going to happen?
these 0 x.
It'll be 0, start accumulating at negative 1. So there'll be a 0 at negative 1. Okay, let's graph the rate. So here's our rate function. This accumulation function, how many rate functions does it have? This accumulation function, how many rate of change functions does it have? He says 1. Agree with that? Yeah, there's only 1, right? At any, we'll pick this up Wednesday. For those who came in late, tomorrow's recitation is going to be optional problem session of the homework that was due Friday and today, and then we're turning in all that Wednesday. Okay? So if you want to just work further on those in groups, I will be there. Marissa Bell will be there, and we'll be there to help you. And then we will turn all those problems in on Wednesday, in addition to some new homework that I will post on this stuff. Okay? So, optional recitation. All the optimization problems are due Wednesday in class.